I will begin, hopefully not with a sneeze. We shall see. All right, with prayer. That's better. Dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Pray you'd help us to use this time wisely and just to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. Okay, so let me get my book. It's kind of a nice time in the semester. We've pretty much covered all of the major theoretical things that we're going to do this semester. And I think for the most part, from this point out in lecture, we're just kind of fleshing it out. And, you know, I might go back. I did want to give a proof of partial fractions because I think it's interesting that that's something you can prove. So I still need to sit down and work it out for myself so I can show it to you guys. But that was back in chapter 4. I never covered that though. Anyway, do you guys have questions about? Or boot? Section 3.4, number 30 and 2. Let's see here. So we're supposed to prove the second isomorphism theorem. We have A, an ideal of R, and S, a subring of R. What else do we got here? So that's an if. Then S plus A is subring, all right. Comma. A and S intersect A are ideals of the ring S plus A, I suppose, and S respectively. Okay, fine. You got me. What else? And S plus A quotient by A is isomorphic to S mod S intersect A. So you've convinced yourself that S plus A is a subring, and that those are ideals. That's all good. It's just the isomorphism. Yeah. So I think, excuse me, we want to write a. I'd assume we're looking for some sort of map from one to the other, which takes A as its kernel, right? I mean, usually the second isomorphism, this is number 32. Section, what was it? 3.4. And the proof of the second isomorphism theorem in our previous work on groups was born of the first isomorphism theorem, right? And just the appropriate map. So let's see here. I should be looking for some kind of map from where to where from. Yeah. Right. So What's a typical element in here look like? Uh-huh. And so what can I map that to? How about S plus A plus S intersect A? Does that work? Excuse me. Goodness gracious. What's that?
So we don't know that S plus A is an S, right?
Um, um, yeah, I mean, well, definitely. So that's not going to make sense because, like you said, S plus A doesn't have to be an S. So fine. Let's try for S plus S intersect A, yeah. Then that begs a question, which is that well defined? Right?
It'll get everything in S.
Yeah, that if this makes sense, it's clearly a surjection. The question is, does this mapping well defined? How do we check that? Well, suppose we have S1 plus A1 equal to S2 plus A2, right? And then we want to study, is psi of S1 plus A1, as we've defined it, equal to psi of S2 plus A2, right? Oh, yeah, I mean, this is fair enough. That's equivalent to asking the question, is S1 plus S intersect A equal to S2 plus S intersect A, which of course is equivalent to asking the question, is S2 minus S1, an element of S intersect A, right? Why? Uh-huh. Right. So you go back over to here, our assumption, and so you said S2 minus S1 is equal to what? Right. And that is the difference of things in A, which is an ideal, which of course is a special kind of subring, right? Well, sub-RNG. Because there's no assumption that 1 is in there, right? So that's an A, which says that that's, excuse me, I have problems. I mean, I have that, I'm sorry, but this is also you're right, I see what you're saying. So these things are in the intersection because they're in both, yeah. You're telling me that. I wasn't, I think you are already saying that. I just took me a while to get what you're saying. So, yeah. So what's that mean? So at least it's a well-defined map. Now, the question is, what's that? Is that clear? The kernel. So let's see. Let me just write it down. S plus A is in the kernel. I think you're right. Kernel psi, if what?
Psi of A, or yeah, sorry, S plus A is equal to S intersect A.
Right, which is interchangeable with S being an element of what?
Oh, yeah. Yeah, S is an element of S intersect A. We already know it's an element of S. Which implies S has to be on. Then is the kernel all of A?
Yeah, because we're mapping from S plus A, but if we're only looking at S's, then we're also using A.
Like A1.
So the okay. So that says that S. I see what you're saying. That says that S has to be in S intersect A, which means that S has to be in A. So then S plus A is in A again, which is to say that the kernel is A. Because of course you can also take S equal to 0 to get that arbitrary. I mean that tells you that the kernel is a subset of A. To see that the kernel includes all of A, just take S equals to 0. Then you got psi of A equals S intersect A for arbitrary A. Right? Yeah. Okay, so I'm on board. The kernel of this map is indeed A, right? It's on 2, right? Yeah, we need, but we need ring homomorphism too, right? So we're supposed to check. So we also need psi of I believe we need psi of 1 maps to 1, right?
Oh, yeah, we do.
With psi of what? S is a subring, so that means it's got 1 in it, right? So
Right.
psi of 1 is equal to 1 plus S intersect A, which of course is the 1, quote unquote, for this, for this thing. Stupid. Anyway, that's 1 in the, that is the 1. Okay, great. What else do we need for ring homomorphism? 1 maps to 1.
You could do psi of S plus A times psi of, or yeah, S1 plus A1.
Oh, you want to do the product first?
Yeah.
Okay.
S2.
Okay. So that's psi of S1, S2 plus S1, A2 plus A1, S2 plus A1, A2. Now, at some point, we need that A is an ideal,
Yeah, I
right?
was going to say, but A is an ideal, so you can just absorb the S1, A2, and the A2, yeah, all in A.
Right. So this is just equal to,
S1, S2 plus S intersect A.
right?
But yeah, you can break up the,
Which is equal to, oh, I'm sorry. Duh. Right, yeah.
and then you want to do psi of,
Yeah, we should also check additivity, right?
yeah.
But that's almost the same. I won't write it down. I mean,
Do you have to do subtraction? Or
I think should remember these things, you know?
Just addition,
Excuse me.
Subtraction.
Addition, multiplication, and 1 goes to 1. Yeah. By the way, for a general ring homomorphism, you just need addition, multiplication, and that's it. I believe so. There's no
because if there's no identity.
no identity, and that's important because I don't know if I sent this correction out, but mission 10, the first problem I say show something's a ring homomorphism, but Kang pointed out it doesn't make sense because it doesn't send 1 to 1. Like you take the identity matrix, feed it to my homomorphism, it spits out 0. 0 is not the 1 for the integers, so. But it does map 0 to 0, and I do think that mapping is. I know I still need to think about that. The first problem on mission 10 might have some trouble. So I would skip it if you're there already.
I was really worried about that one, but can you give us a hint on a mission problem?
I can try.
Speaking of mission, okay, it's mission 9, 4.328.
4.3, number 28, you say. So f is a field. H is not equal to 1, a monic polynomial in the polynomials over f. Show that every element of f of x mod the principal ideal generated by H is either a unit or a nilpotent if and only if H is equal to p to the n, where p is monic and irreducible. Well, let's look at how this works out before we try to do anything. So an example of this would be something like, take r of x, mod, I don't know, x squared, yeah, maybe that. Seems like that would fit the thing going on here. We're supposed to look for a h not equal to 1, all right, and h is equal to p to the n, where n is greater than or equal to 1, and p is monic and irreducible. So f of x, and here here I'm suggesting h equals to x squared, p is equal to x. So p equals to x is monic and it's irreducible. Linear factors cannot be reduced, right? Maybe I should do something more exciting than this. Let's do, at least stick with that. Let's do that. So what's that look like? Looks like things of the form a plus b x bar, such that a and b are in the reals. And here x bar, well, this notation, a plus b x bar, is a plus bx plus the ideal generated by x squared. Okay, so that's just a shorthand. And so long story short, the deal is that, I mean, I don't want to, well, I guess I can get, let's see here. So, goodness gracious. How about, what happens if we look at x bar times x bar? What's that equal to? Right, but using, I mean, just, I'm trying to explain what. So that's you're fine. That's supposedly 0 plus 1 times 0 plus 1 times x, right? Plus x squared. And 0 plus x plus this, right? Which by definition is x squared plus x squared, right? Which is equal to x squared, which in our current language we could call, maybe we should call it 0 bar. I mean, so my point is that this x bar, it satisfies it basically forces this polynomial to be 0. If you trade x, I mean, in this, some people would just use an x here and say it's like that with x squared equals to 0. I mean, that's a useful calculational simplification. I'm just putting the bar there so I can be a little bit more true to our construction, But you could think of it up to isomorphism as a plus bx such that x squared is equal to 0, right? All right. So the point is, this is what things in this, I'm sorry. I'm so sorry. You guys should be confused, right? I meant this thing. Polynomials are not just that. Polynomials go on and on. But in that factoring, you got objects of that type, right? So if you have a plus b x bar, right, times c plus d x bar equals to 1, right? What is that? What, for a given, when can I solve that? Well, this is AC plus BD, right, plus BC x bar equal to 1, right? Because the x bar squared is 0. What's that? Did I do that wrong? AD? Oh, yes, thank you. Yeah. So sorry. So that shows to me that I need to make this give me the 1, and I need to make this 0. Right. So, yeah. So apparently we need what? A not equal to 0, right? Then we put C equals to what? 1 over A, right? And then that gives us AD plus BC equals to what? Well, A times D plus, what was my C over A, right? Equal to what? Equal to B over A? Oh, thank you. Sorry, B over A. Now that should be equal to what? That should be equal to 0. Now B is given, right? D is what we're trying to find. You should think of it that way. This is given. Does this exist? If so, when? I mean, that's the point of this calculation, is to find out when is A plus BX bar a unit. That's what I'm trying to do. Sorry, I didn't explain myself. So this, we can calculate. D is what? D is equal to minus B over A squared, right? So therefore, A plus B x bar inverse equal to, excuse me, 1 over A, right? Minus B over A squared x bar. which by the way is very, very satisfying if you think of it this following way. See, this is really a plus b x bar inverse. We can look at as a inverse times 1 plus b over a x bar inverse, right? Which is equal to a inverse times 1 plus b over a x bar, well, minus 1 over b x bar, and then plus stuff, geometric series. But the geometric series truncates at linear order because it's nilpotent. The x squared is nilpotent, and so we just get this. Anyway, that's the so that's if it's a unit, that's what it looks like. What's the condition for it to be a unit? Yeah, a not equal to 0 gives a plus bx bar in r adjoint x mod x squared units, right? So what if a is not equal to 0? I mean, if a is equal to 0, then it's not a unit, right? Right, so if a is equal to 0, then we have things of the form bx bar, right? Which, of course, if you square it, you get 0. It's nilpotent. So everything in this is either a unit or it's nilpotent. So this question is asking you, can you show that using just that? You're building your factoring by quotienting by h, where h is a monic irreducible to some power, right? I mean, so you're supposed to do f of x mod h, right? Where h is equal to equals p to the n, right? Well, I mean, to start with, I mean, there may be a more slick way to do this, but I think I can more or less calculate as I did this example to show that. You know, if h is p to the n, and p has you know, p is monic and p is monic and irreducible, right? So suppose the degree of p is equal to k, just for the sake of discussion, which is greater than or equal to 1, right? Then h, what's the degree of h? Yeah, k times n. K times n. So one way I could think about doing this problem, and I'm not sure that this is the right way to think about this problem, by the way. So, you know, this, if you take f of x and you mod by, you know, h, what's this look like? This looks like things of the form, what, you got, you know, a sub 0 plus a sub 1x plus a sub 2x squared plus plus a sub what? A sub nk minus 1 x to the nk minus 1 plus what? Plus this, right? such that the a sub I are an F. I mean, that's what that is. See, because, of course, anything higher order can be reduced because we have that H is monic, right? So if I have x to any power larger than nk, well, nk are larger, then those things can be absorbed into the ideal, the principal ideal generated by H. So that's a typical representative in that space. So then we just have to show that those things are either units or nilpotent.
Finding an inverse for one of those is a lot harder than our example.
Is it?
Is it not?
I don't know.
It looks like
Well, it seems to me that if there's not a, if the constant term is 0, I can see just from looking at it. If the constant term is 0,
then we know
it's nilpotent. So on the basis of the example we just did, I would expect that you can prove that if the constant is non-zero, an inverse exists. And on the other hand, if the constant is 0, it's nilpotent. And that's a dichotomy. It's either one or the other. So that would prove everything in there is either nilpotent or a unit. Now there may be some slicker way to do this, but that's the way that occurs to me at the moment. And to show that there's a formula to find the inverse explicitly, You notice that I haven't really used it's hard to see where I use the irreducibility of x in my example. I might need to do an example with a higher order irreducible to really gain intuition for what I should do. That's how I'd start, anyway. But again, I don't know if that's the right way or not, but there's a possibly useful hint. I don't know.
yeah, I think it is. We also have to do the other way, like it's an only. I did start on like the way like so you assume that every element in there is a unit or no potent, and then you have to show that H equals P to the N.
I don't know. Not yet, anyway. Or I know, I just won't give you a hint. Yeah, that's what it is. I know everything. I'm a teacher, right? So, no, not actually how it works, right? I'm sure you guys already checked the back, huh?
Yeah.
Yeah.
I think that was helpful though.
Are the resident experts helpful?
I haven't asked.
Okay.
I don't think Sam had gotten
This problem is actually very interesting now that I look at it again. I mean, I often think of, my sort of naivete is to think of rings as either having nilpotent things or units. But you can have, I don't think it has to be an either or. I mean, there's integers, 2. 2 is not nilpotent, and it's not a unit, right? So, but anyway, you guys have other questions that yeah, I mean, for me to be more helpful here, I'm just going to have to basically work it. I don't have a kind of any. No, we can stop here for today if you want. I wouldn't be opposed. I'm kind of tired. So,
It's close to 6 anyway.
yeah. Thanks, guys.